great question. So like I've lived in Miami and I've lived in Las Vegas. In Las Vegas, there's no humidity. So you can just run at, higher fan speed and it's all what we call sensible cooling. All we're doing is changing the temperature of the air. And if you talk about equipment, if you ever put a piece of equipment in for a customer, a high-end piece of equipment, and sometimes they'll say, hey, it's not dehumidifying as well, because to get these numbers, these performance numbers, they get it off of sensible cooling. In other words, just changing the temperature of the air. But the big factor of comfort is the humidity. So when you slow the fan speed down, you're actually moving less air. It's making the system overall less energy efficient, but you're getting a better comfort level. So when you slow the air down, the air is moving slower, so you have less heat in the air. So as the temperature, you have less heat, so that's less temperature. So as you have less temperature across your evaporator, what does your pressure do? If you had less heat across your evaporator, what would your suction pressure do? It goes down, yes. So as we're slowing the airflow down, we're slowing the amount of heat we're trying to absorb down. And as we slow it down, we have less heat acting on it, so the pressure drops. And when the pressure drops, what else drops? The saturated temperature, the boiling temperature of the refrigerant. Now, the reason that's good for dehumidification is the refrigerant's boiling at a lower temperature. That means it's lower than the dew point temperature. So we're more likely to have condensation, just like when you have the tea glass and you have one that's full of ice right there and it's sweating like crazy, and you got one with just like all the ice is gone, but it's still cool and it's not sweating as much. So the lower this is below dew point, the more dehumidification we're pulling. So we're literally we're still moving the same amount of energy, but now we're taking it and changing it from water vapor in the air, making it change state from a vapor to a liquid. We're condensating that moisture on the evaporator coil, and that moisture collects in the drain pan, and that's running outside. You can literally take a bucket and you could put it under here and see how much water you get in 1 minute. You can multiply it to an hour, and you can find out how much water you're moving in an hour. And because the moisture in the air is changing state from a vapor to a liquid, it's latent heat or hidden heat, right? So now we're changing the temperature less. There's less temperature change, but we're taking moisture out of the air, and that takes BTUs. For 1 pound of water to change from a vapor to a liquid, anybody know how many BTUs that takes? 970 for 1 pound of water. How much is a pound of water? Anybody know? If we had a full one of these, that's about a pound of water. So if every hour to get one of these, that's 970 BTUs of energy just to take this out of the air. So that's what we call latent cooling, because it's literally cooling. It's pulling the moisture out of the air, but we can't sensibly measure it with a thermometer. But it's a big part of the cooling. So as manufacturers want higher and higher efficiencies and higher fan speeds, we're doing that by getting the sensible change, but we're getting less of this out of the air. But what do we sell? We don't sell temperature, do we? Yes, absolutely right. We sell comfort. And part of comfort is pulling that humidity out of the air. Actually, as we cool air off, it becomes more dense, and we actually end up with a higher humidity. If we only cooled and didn't dehumidify at all, the humidity in the house would go up. If you walked in walk-in coolers, you'll see that. So we must pull that moisture out of the air. So as we do that by slowing down the fan speed is a good way to doing it. We're sacrificing some sensible capabilities, and we're putting in the latent. You may have heard somebody say, well, your delta T should always be this one number that somebody made up. Well, that number changes by how much moisture we're removing. And that number is going to be different in Las Vegas versus here. Now the key is, if you're going to slow this fan speed down so that we get better dehumidification, better latent cooling, we have a limit at how slow we can slow it down. What is it? Regardless of what our CFM is, what is that limit? Anybody know? As we drop the temperature of the air, what else is dropping? Pressure. And as the pressure drops, what else drops? The saturation. Yes, the saturated temperature. Yes, dude, that's exactly right. Yes, this guy, yes. So regardless, we always want to be watching our suction pressure. I don't care about pressure. I want to know even though I'm checking it here, I want to know the boiling temperature, saturated temperature inside. I want this to always be above 32, otherwise we're going to freeze. Yes, we don't want an ice machine, we want an air conditioner. So if you have a brand new filter and you're right there at 32, what happens if that filter gets a little bit dirty? Yeah, you're closer to freezing. So when we talk about slowing the fan speed down, it's good to an extent. You got to be looking at all your conditions. What if that customer has a very small return air? Like the return air it can barely get enough air. Well, now we got to look at the bigger picture. We're going to have to up the fan speed to keep it from freezing, right? This is why we look at CFM. CFM is a good number, but also it's a whole system. The airflow is a key part of that, but it all ties in together. Tomorrow we're going to be talking about charging, and that's all going to play in. Does that answer your question?
Yeah.
Sorry, I went a little far, but I like to bring it all back. Hopefully I brought it back in for you.
So you really need to gauge and make your sacrifices based on like what the customer like wants. It's like, I could deal with it being warmer, but I really just don't want the humidity. So like it's up to them really, and you just gotta make it happen.
Yep. And also it increases runtime. So as we're using less sensible cooling, the house doesn't change temperature as fast, so it gives us longer run times. And the longer that we're pulling air across there, the more dehumidification we're doing as well. So yeah, be sure you're thinking not just temperature, but also humidity. That temperature, humidity, dew points, those are great things. When a customer says, hey, I want it to be at what temperature, I always respond with, and what humidity? So I want that customer thinking about the humidity also. So when they're thinking, oh, I'm comfortable at 67 degrees, at what humidity? I'm comfortable at 80 degrees, at what humidity? The humidity is a key factor. I've had houses before that were 80 degrees and they were super comfortable with the fan moving. I've had other houses that were at 68 degrees and the customer's unhappy that it's always hot. What was the difference? Humidity. 80 degrees and it's like 5% humidity with the fan running. The evaporation is your cooling. That's your air conditioner. The moisture from your skin is changing state. It's absorbing 970 BTUs for every 1 pound of water evaporating. It's literally evaporative cooling. Your body has a built-in air conditioner. Like, how awesome is that?
Would adjusting the fan speed also help with like coils that sweat externally and like supply duct work that sweats through like insulation?
Well, that now we end up at another factor. If you have the ductwork, as you slow the air down, the air is now going to also be a lower temperature. So now that lower temperature air, especially in a cabinet like this, you only have 1/2 inch of insulation. And if this is in an unconditioned space, like it's outside of the building envelope, in the attic or in an unconditioned basement, you can now have the cabinet itself sweating. And now you have another problem, and there's solutions such as you could raise your fan speed back up, or you could add insulation on the cabinet. I've taken and insulated entire air handlers in the attic before so that they didn't condensate. But yeah, there's always that cause and effect. But if you're looking at humidity and you're thinking, hey, this cabinet's sweating, that means the cabinet's below dew point. Just like the evaporator's below dew point, it sweats, now your cabinet's below dew point. And if you have a psychrometer and you're looking at humidity, you can look at dew point also. They said, hey, my windows are sweating all the time. Well, if you look at the temperature inside the house and the dew point inside the house versus the dew point outside, if the outside dew point's at, say, 75 degrees and the temperature of the house is at 70 degrees, well, yeah, the windows are going to condensate. It'll be like the tea glass. The windows are literally the tea glass. It's below the dew point. You're going to have condensation. So you could raise the indoor temperature of the house up, and that's doable if you keep the humidity in the house down. It makes it feel more comfortable. See, it all ties together. Like I love HVAC because it's like never-ending knowledge.
And if you want to learn more about HVAC, make sure to check out our website over at acservicetech.com, where we have a bunch of quizzes, articles, and HVAC books for refrigerant charging and mini splits and other various resources. Hope you enjoyed yourself. We'll see you next time at AC Service Tech channel.